Hello. Today I'd like to go over the finding the convex hull using the Quickhull algorithm. This is one of my favorite algorithms, and what we'll be doing is we'll go over the theory and the algorithm, and then secondly, we'll go over how to implement the algorithm. For me, those are two separate skills, and my intention is that at the end of the video, you'll understand the algorithm, and also you'll be able to implement the algorithm for finding the convex hull using Quickhull. Okay, so let's go over the algorithm here. So Quickhull is a method of computing the convex hull of a finite set of points in n-dimensional space. It uses a divide and conquer approach similar to that of quicksort, from which its name derives. Okay, that's basically the gist of it, and let's get started on the algorithm here. So it says find the left and rightmost points. Okay, so let's do that. So our goal is to come up with these points in yellow, but we first start off with a set of points, and we find the leftmost and the rightmost point. One thing of note here is that they ask us, well, we always know that these maximum and minimum x value coordinate points will be members of the convex hull. They also ask or point out that if many points with the same minimum or maximum x exist, use the ones with the minimum, maximum, y respectively. So I just want to make that, I want to just stress that sentence there. And so next point or next step says to use the line formed by the 2 points to divide the set into 2 subsets of points, which will be processed recursively. So we have a line segment created by these 2 points, and we partition these points. Okay, so what next? Determine the point above the line with the maximum distance from the line. This point forms a triangle with the 2 points on the line. All right, so what we do is we loop through all the points on this one side, and we find the farthest point. And basically we want to find the orthogonal distance from the line segment formed by these maximum and minimum points. And once we have that point, that creates a triangle. The points lying inside of that triangle cannot be part of the convex hull and can therefore be ignored in the next steps. So I wanted to point out that this point here, this point that forms the triangle, is now a member of the convex hull. And recursively repeat the previous 2 steps on the lines formed by the 2 new sides of the triangle. So as they mentioned, now we need to find the farthest point from maybe this segment and this segment. So let's start with this segment to the left. And while there's only one point, in any case, we find that point, and now we form another triangle. Now that point is now a member of the convex hull. Doing the same thing on this for this last side over here. We find the farthest point and form a triangle. Now this point is also a member of the convex hull. Moving on to the green points over here, we find the farthest point, and now this forms a triangle, and we could ignore these internal points of the triangle and focus on these external points here and find which one is farthest. Forms a triangle. Now this point is now a member of the convex hull, and the same thing here for this line segment here. Find the farthest point from it. There's only one point. Nevertheless, this last point becomes the last member of the convex hull. So now we have this here, and that's our goal, is to find these points in yellow. Okay. So that's basically the entire algorithm. For me, what drew me to the algorithm was just how, maybe even the animation, just how we can just divide the points and and the algorithm looks simple and beautiful. In any case, let's go forward and implement it. Okay, so I do have some, at the end, my goal is to compare the Convex Hull implementation by scipy to our implementation, and hopefully we get similar results. Okay, so let's start off with the implementation. So let's start off with something simple. We have nothing, so let's start off with the Quickhull, and we'll accept the points. Okay, so the first part of the algorithm says to find, well, if we use pseudocode, find the left and rightmost points. Okay, we can do that. Okay, so let P and Q equal find, maybe we'll call it maybe min and max points. Now what I like to do is pretend these functions are implemented and implement it at the very end. So let's just pretend these functions already exist. We know these points are members of the convex hull, so let's add them there. Okay. Next, what do? We segment AB, divides the remaining n minus 2 points into 2 subgroups. Okay, so let's do that. So remember that was where we divided them into these red and green points here. So there's red and green. So that's what we're going to do. So we'll just call this function partition points, and we'll pass in the points and P and Q. These are the points that, these are the minimum and maximum point that will create the segment that will be the determiner of how to divide the points. And we'll call this above and below. Notice here how I use the unpack operator. Some may call it the spread operator, and some may call it the splat operator. However, I think Python calls it the unpack operator. So we'll just go with that. Moving on. Once we have the above and below points, as we do over here, we recursively pass the points into a helper recursive function, and we'll call this find hull. So maybe find hull. So we'll pass in the hull, we'll pass in the above points and P and Q. And the same thing over here, pass in the hull, but now we'll use the below points. But now we do something interesting here. We reverse them. So why do we reverse them? Well, first of all, that's what they ask of us according to the algorithm. But the question becomes then why? So imagine if we're standing upright and I tell you go to the left. So you pick up your left hand. Now imagine you're upside down. And if I were to tell you to go to the left, it would actually be the opposite. So when you're upside down, I would have to tell you to go to the right. So that's basically why we have to invert these, because we remember as we perform this algorithm here, remember how we're looking above it, but when we're upside down, what does above it mean? So that's why we have to switch the minimum and maximum. And I just hope that makes sense. In any case, moving on. So once we're done with these two recursive functions, we just return the hull. Okay, so this is about 1/5 of the entire code. So now let's move on. Let's first start off with this find min max. So define find min max. Now I want to make this clear. So when we find the min and max, we do not need to sort it. All we need to do is perform a linear scan and record which is the smallest and which is the largest, or minimum x and the maximum x. Also remember though that if there's a tie, we use the y value that's minimum for the minimum x value, and the y value that's maximum for the maximum x coordinate. So let's initialize those. So I just like to keep it simple, and I'll just say points 0, 0.0. So I initialize the minimum and maximum to the same thing initially. So because I've used this first point, I can start off at the next index. And let's find the minimum point. So we'll say if x is less than min of 0, this is our minimum point, or x equals the current minimum, and y is less than min of 1, then we'll just update it. Okay, moving on to the maximum point. So if x is greater than max of 0, or x equals max of 0, and y is greater than max of 1, we'll update it. Now, maybe a good question to ask is, why do they have us do this? So let me give you an example here. Suppose we have points like this, star, star, star. Actually, I don't even. So suppose we have points like this, just suppose. And also suppose that we have, this is our minimum here, and this is our maximum. So we just chose that. It just so happened by chance that these were the points that we selected. And they are our minimum and maximum. However, notice that because they're on the same line, that we're not really following along with the divide and conquer nature of the algorithm, because our goal is to divide these points as much as possible so that our processing time is minimized. So notice here, if we pick these 2 points that have the minimum and maximum x coordinate, that all of the points, all of the remaining points, or at least mostly, do not get partitioned. So it would be better if we had something like this. So then we would at least have an angle, and then this would be a better partitioning. I hope that makes sense. Okay. And again, they also, to stress it, they also maintain that we should do the same thing. If many points with the same minimum maximum exist, use the ones with the minimum maximum y respectively. So that's what we're doing. Okay, so we have completed implementing this subfunction required for the algorithm, Quickhull. Now let's perform the partition points. So how do we do that? Define partition points. So we'll pass in points. Now, since we're using this unpack operator, on the other side, what happens is we end up with something like this. Okay. And now let's initialize our above and below. And now let's loop through the points and find which points are above and below. So I'm going to use this formula here. If you'd like to know how this formula came to be, or where I got it from, if you look in the description of this video, I will post a link to another video of where I explain it. But basically, you can use the cross product, the cross product used in either calculus or linear algebra, and that's just how the formula is derived. But as I mentioned, I'll be attaching a separate video in the comments that goes over how to determine if a point lies above a line or below it. Okay. And now if this point is below the line, sorry, less than 0, we'll attach it to above. Maybe I'll do this here. Okay, so d equals x1 minus x times y2 minus y minus x2 minus x. One thing I want to point out is notice how this formula is, how I would say this, how can I say this, like order sensitive. So I just want to point that out. Now else if d is greater than 0, we'll say below dot append xy, and then we will return each of those. Okay, let's make sure this is good to go. Looks good. Looks good. Okay. All right, moving on. So now we're left with implementing this function, so we're getting close. So define find hull. So it accepts hull and the points and a like minimum and maximum. Okay. So this will be a recursive function, therefore it needs a base case. So the base case will be if there's no points to process, we can just return. So if length of points equals 0, we can simply return. Otherwise, if you recall from the algorithm, we needed to find this farthest point. So let's do that here. So we'll say r equals farthest from line, and we'll pass in all the points, and this is the line segment defined by these 2 points. Okay, and we'll define this function in a moment. But once we have that point, we can add it to our hull. And next, we'll partition these points again. Remember, as we did over here. So once we have this triangle, we need to partition. For this segment, we'll partition these points. And then for this segment, we'll partition these points. Remember, once those points are partitioned, the points lying inside of that triangle cannot be part of the convex hull and can therefore be ignored in the next steps. Okay, so let's do that here. So we can take advantage of or reuse our partition points that we defined earlier. So that's great. That's good engineering. And now we'll say, okay, so star P. Now what's our endpoint? Star R. Very good. And this will be above 1, and we'll call this below 1. Now moving on over here. Now what are our 2 points here? So now if we look at our basically according to the algorithm, once we find this farthest point C, so notice how these are situated, and it should make sense if we look at our maybe, I don't know, say our animation here. So once we find this point here, so notice how this minimum is still the minimum, but this is like basically like a midpoint. So when we call this, it would be something like star R star Q. So I just want to point that out. Okay. And then what do we do next? Now we make our recursive call. So this is this point of the algorithm here. So now we just find hull with this situation, or with this setup. Okay, so we say find hull with hull and above 1, and our new endpoints will be P and R, and find hull will be above 2. We'll call it R and Q, and we can spell this correctly. Sorry, need to update these over here. Now notice though, We don't use these two, the below here, because they're inside the triangle and they will not be part of the convex hull. So in order to be more Pythonic, we can maybe just change this to underscores. Okay. Now that's a little bit more Pythonic. Okay, great. Now we're down to defining this function, farthest from line. So let's do that. Let's do that here. So define farthest from line, which accepts points and the 2 points that form the segment that'll be used for finding the longest from that line. And I want to make this point, it's called the orthogonal distance. Okay. Okay, so let's do that. So we'll just set it equal to 0. This will be the distance. And we'll say, okay, for r in points, and we'll want to say, we'll write a function for that. We'll say distance from line. And we'll pass in star r, star p, star q. And we'll set this equal to the distance. For distance from the line, there, again, I'll have a separate video for that as well. But it's basically, you can Google it, but it's basically this formula here. And again, I will have a separate video attached in the description that will link how this formula is derived. Okay, so let's move on. So where are we? Okay, so once we have this distance, we'll say if the max distance is less than it, or the max distance equals it, and the x value is less than the current x value, or the maximum x value, then we can update it. So max, this will be the distance, and the max point will equal r. Okay, and then we can just return the max point. So return max point. Okay, lastly, we need to define this distance from line function here. So let's do that. Define distance from line. And the unpack operator says we'll have this type of input. Okay, so I think I already showed that, but yeah, again, I'll just mention it again. We're basically just using this formula, and I'll have a video for how this formula was derived. Okay, so let's go over that here, or implement this function. So we'll say calculate the line coefficients A for the equation this is called the general form of a line, or yeah, general form of a line, or general equation of a line. I think it's general form of a line. In any case, here we go. So A equals y2 minus y1, B equals x1 minus x2, and C equals x2 times y1 minus x1 times y2. Okay, and then we'll return the absolute value of A times x plus b times y plus c, all divided by a times a plus b times b, all to the square root. Okay, let's check that. Just make sure there's no mistakes. Looks good, looks good. x2 times y1 minus x1 times y2. ax, by plus c, a. Okay, this is good. Okay, so I think we are done. I think we are done. Yes. Okay, so we're done. So now what do we do next? So now that we've implemented it, it only makes sense that we should test our function. So scipy already has a Convex Hull implementation, and I think it'd be fair for us to compare our implementation against theirs, just to make us feel better that our work is just as good as theirs. Okay, so let's go over this here. So I've written some test code here. Okay, and let's just go over it. So I'm gonna make some random points, random integer between 25 and 400, x and y, and I'll make 200 points. And so here's our implementation, and these are the results. Their implementation is slightly different. They you pass in the points to their class here, and then you call the vertices, like you get that instance variable, and then what they do is they give you indices from the points. So that's what we do here. We extract the points from the index that they give us. And so what we'll do is we'll compare that we have the same points and their lengths are the same. If this doesn't work, then well, we'll print fail. So fingers crossed, hopefully we don't fail. So let's open up the terminal and let's run Python. What do we call this? Quickhull 3. Okay, great. So it didn't fail. So that means we're doing well. So I'm just gonna run it. Let's run it a few more times. So I'm gonna run it about 5,000 times. So for in range 5,000. And let's do all of this again. So we'll say, and this will make us feel very good that our implementation is good to go. So let me make sure I set that up correctly. So 5,000 times, and we're getting random points. Okay, yeah, everything looks good. So fingers crossed. It may take a while while it runs, so bear with me. Fingers crossed that it never says fail. Okay. So let's run it. Okay, no error so far, so that's good. That's good. I'm pleased so far. Still running. Maybe 5,000 was too much. Okay, looks like it's done. So, high five, everybody. Looks like our implementation is just as good as scipy's. Okay, so we're done, and I really hope that you enjoyed this, and I hope that you learned something. If you found this video helpful or beneficial or educational in any way, please consider liking or subscribing. Other than that, have a wonderful day. Take care of yourself. Cheers.